Okay, well, the chat says go ahead, so I will go ahead. Thank you very much. First, I'd like to thank the organizers for inviting me to speak in this workshop. Then I would like not to thank Austrian Airlines for keeping me at the airport yesterday for 10 hours until eventually I couldn't fly. Nevertheless, I am really happy that Norbert could find this great solution that allows me to give this talk after all now. And it's not ideal because I really wanted to be there with you and interact with everyone. But yeah, that's life. And as a theoretical physicist, I don't even pretend that I'm trying to understand it. So I will go ahead. I think I can't hear anyone. So please, if maybe, I don't know, you can say something on the chat if there is a question. And once again, I'm really, really sorry that I give it this way. So I'm going to tell you today about a kind of tensor network states which are called gauged Gaussian Fermionic PEPS. It's a way to study lattice gauge theories using tensor networks, and it's really a very long ongoing effort, which has been happening for quite a few years now. So I think that quite a lot of you have heard different versions of it, and every time something else is accumulated and accumulated. And let's begin. So basically, why am I interested in gauge theories? They are interesting for many reasons in physics. They are very central. First of all, in the context of high-energy physics, as we know, they provide the framework for forces and interactions in the standard model. And in condensed matter physics, they appear too. They can be in some effective or emergent models. They appear in some theories that might explain ITC superconductivity. And many, many, many field theories actually show this local symmetry. So yeah, these gauge theories are very interesting in many contexts of physics. On the other hand, they are also very, very challenging because at their core, there is a local symmetry, which is what makes them so suitable for PEPS, as I will mention. But the local symmetry means that we have many constraints that we need to deal with a constraint per lattice point or per point of space if we are on a continuum. They involve a lot of non-perturbative physics. For example, one very famous gauge theory is QCD, the theory of the strong nuclear force in the standard model. And there we have this phenomenon of quark confinement, that the quarks can't be found as free particles in nature. They confine each other to bound states. And this has to do with this highly non-perturbative effect called confinement. So overall, these gauge theories can be very hard to treat experimentally. For example, in this case of very strong forces, they are very hard to treat analytically because they involve a lot of non-perturbative physics. And then very clever people in the 70s came up with the idea of putting everything on a lattice. And first of all, in a way that allowed to do some better regularization, which is gauge invariant, but also later on to do some numerics. So in conventional lattice gauge theory techniques, the idea is that both space and time are discretized. And when you go to a Euclidean space-time, you change to imaginary time, you do a weak rotation, then you can use in the path integral formulation, you can express any expectation value that you want and in the form of some statistical sampling, some statistical mechanics integration, and you can use Monte-Carlo to calculate the integrals and calculate almost anything you want. And why am I saying almost? Because while this has been very, very successful and produced a lot of great results for many applications, for example, the hadronic spectrum, the spectrum of particles in QCD, it still faces two very major problems. One is that when we go to Euclidean time, to imaginary time and the Euclidean space-time, we can't look directly at real-time evolution. The unitary operator, the unitary evolution operator becomes a decay factor. And while this is very nice for finding ground states, it doesn't allow us to look directly at time evolution. The other problem, which is rather more technical, but very important, is the sign problem, which occurs in many important cases where we deal with fermions, with dense fermions, with finite chemical potential. In such cases, what has to be ate as the probability density is no longer positive or real, and the Monte-Carlo description fails, and one has to do something else. So this is a really nice place to use some ideas from quantum information, quantum simulation, quantum computation, and tensor networks techniques, and I'm going to tell you a bit about it today, what we do. Because basically, okay, real-time evolution is something that, right, it's a big issue to do real-time evolution with tensor networks, but it's not something which is prohibited as in the case of Euclidean space-time or imaginary time. So this is not something which is a priori impossible. The sign problem arises in this path integral formulation because of this very particular technical way we treat the fermions using Grassmann variables and so on. But when we do it with quantum Hilbert spaces and fermions are represented as fermions and we don't compute through this Grassmann machinery, we might have a way to go around it. So these are two good motivations for looking at tensor networks. So actually quite a lot of work has been done with tensor networks for lattice gauge theories, and I'm sure that most of you are familiar with most of this. So I don't have to tell this audience that in one space dimension with MPS and DMRG, you can compute quite a lot of things. And this has been extended also for lattice gauge theories in one space dimension by many clever people. And it started from benchmarking some known results to actually looking at problems which face what we discussed earlier. It was actually proven to deal very nicely and efficiently with finite chemical potential, which otherwise would have encountered the sign problem, and with real-time evolution phenomena that were demonstrated. So it's a very powerful tool. But the question is, of course, how to generalize it to higher dimensions where in general tensor networks might be much more complicated. So if I want to try and map out what has been done for lattice gauge theories with tensor networks in more than one space dimension, I'll try to do it, and I'm focusing, as you can see here with this little footnote, on the Hamiltonian approach, which builds tensor network states in Hilbert spaces, because in parallel there has been quite a lot of research on the Euclidean picture in the so-called tensor field theory. The first works about this topic, I believe, were done by Luca and others who dealt with some pure gauge theories, first Z2 and later on also with continuous groups. And then around 2014, there were some proposals about how to include matter into this picture too, having to do with what's called gauging mechanisms. And one of those I'm going to focus on today. By gauging, I mean, let's take a PEPS or some tensor network state with a global symmetry and try and lift this symmetry to make it local. It's very similar to minimal coupling, which is done usually on the Lagrangian or Hamiltonian picture. You start with something with a global symmetry, you want to make it local, this introduces a gauge field, and we can start talking. So in this work by Yuto and others in 2015, they proposed, I think, the first mechanism for gauging quantum state, for taking some tensor network state and making the global symmetry local. And there, the Hilbert space of the gauge field was similar to the Hilbert space of the matter. So this is suitable for describing Higgs-like theories. And a bit later at MPQ, where I was at the time, we looked at another way which allowed to do it for other types of matter, including fermions. And this is the line of works that I'm going to talk about today. We start with fermions, and I will define everything and explain it hopefully clearly. And In the meantime, there have been some other works, including IPEPS and tree tensor networks, but these are other approaches that I'm not going to enter in this talk. So, what's the Hilbert space that we're dealing with? In lattice gauge theory, in the Hamiltonian framework, only the space directions are on a lattice. We keep time continuous. And we have usually two types of degrees of freedom. We have matter particles, which are mostly fermionic, and they reside on the sides of all vertices of the lattice, which are red here. And then we have gauge fields, which reside on the lattice's links. It's the Hamiltonian picture, so we are dealing with the Hilbert space. And as we will see, it's quite a natural way to describe constraints, as I mentioned, that we have in such theories. Now, probably the most important ingredient of a gauge theory is a gauge transformation. So we have some group, which we call the gauge group, and it parameterizes some local transformations. By that, I mean some transformations which are defined on each side of the lattice separately, and they are parameterized by elements of this group. And they act on a site, the matter field on the site, and the gauge fields on all the links connected to it. States are gauge invariant if they are invariant under each such local transformation separately for each different element of the gauge block. Now, if we have a symmetry, then something is conserved, especially in the case of a continuous symmetry. And so if I look at if my group is okay, so I can define on each side X some gauge transformation parameterized by G, an element of the gauge group, and the gauge invariant states will be invariant under these unitaries for each group element and for each site separately. And if I have, for example, as we often have in physics, a compact Lie group, I can formulate all these transformations in terms of their generators, which can be seen, which can be defined. They are sometimes called the Gauss law operators. We have this set of operators which are simply divergences of what we call electric fields on the links around the site, minus some charge we define on the site, and the states are annihilated by the generators. That's gauge invariance, and the Hamiltonian commutes with all these generators. That's local symmetry, that's gauge invariance. Now, I want to do this with PEPS, and okay, I have this introductory slide. Again, it's probably not necessary in this community, in this workshop. But I do want to focus for a bit on the construction of PEPS, which might be a bit trivial for most or all of you, but I'm doing it to show why it's so relevant for gauge theories. So what do I do? I'm doing it for some fermionic case, because this is what I'm going to use later. I'm looking at a single site, and on a single site, I'm going to introduce both physical and auxiliary degrees of freedom. The physical I denote like this with this orange thing on the side, and the auxiliary or virtual degrees of freedom, these are these blue legs around it. And on each side, I introduce some initial state. It can be some Fock vacuum, for example, and some operator A defined on this side, which creates some state out of it. And then I can take a product of many of these operators A of X acting on some global Fock vacuum of my entire lattice. Okay. Now, what I'm doing, as we all know, I'm going to project all the auxiliary degrees of freedom onto some maximally entangled states, which I denote by these green ellipses. So I have here these projection operators, and I project only the virtual degrees of freedom onto their vacuum. So this might look like a number, but it's actually a state, since here on the right, I have the vacuum of both the physical and virtual modes, and on the left, only the virtual or auxiliary ones. And here in a normal talk, I explain why we have an area law. Again, we don't need it in this workshop. Now, let's recall how we can demand that a PEPS will fulfill some global symmetry, will be invariant under some global symmetry group. What I want to demand, if I want such a thing to happen, is that when I act on the physical degree of freedom, which some unitary that is parameterized by some element of my symmetry group, I want to be able to transform this symmetry onto the auxiliary legs in a very particular way to replace the physical transformation by virtual transformations parameterized by the same group element. And I want to choose projectors, maximally entangled states on the bonds that will be invariant under group actions from both sides. And then let's recall, how do we see that the state is invariant under the global transformation? So suppose I generate some global transformation by a sum of some local charges Q. So the sum over Q is my global charge. I have some parameter here. This is a U1 example, but it can be done for other groups. And I just act everywhere on the physical degrees of freedom with the same transformation. Then if I have this symmetry property, I can move the action to the virtual degrees of freedom. Then since I built the projectors to be invariant, I can just remove them and I'm getting my original state back. And by demanding these two things, I'm getting a state which is globally invariant. Now, how can we use it to create something with the local gauge invariance? So we can have a look on the things that I've shown you so far and see that it's basically pretty much the same. In the case of a lattice gauge theory on the right, I have invariance under physical gauge transformations. I act on the site, and what I have there is called matter. And on the legs around it, the links around it, what I have there is called gauge fields. And I act by some unitary parameterized by my gauge group, and my state is invariant. But in the PEPS case, it's pretty much the same. I act on the matter, and it's equivalent to acting on the 4 legs or whatever number of legs I have around it. So I can interpret it as some virtual Gauss law, as some virtual gauge invariance that the physical degrees of freedom represent the matter, and the auxiliary or virtual degrees of freedom, they represent the gauge fields. So it's very similar, but the difference is that the gauge fields here are not physical degrees of freedom. They are lost in the contraction. They are used for the contraction, but after I contract the state, I don't have them anymore, and only the global symmetry is left. So what I can do is simply take this global symmetry that I have, this virtual symmetry that I have, and lift it to be a local one in this procedure that we call gauging. So what do we do? Let's focus on a single site again, okay? And this is my PEPS, which is defined to satisfy these global invariance properties. Now, the first step of the gauging is that I'm introducing extra physical Hilbert spaces on the links in the outgoing directions where the gauge field will live. And I prepare them in some initial state, for example, a state with no electric field. It can be more general, but let's choose this example. And so far, they are just in a product state with all the other degrees of freedom. Next, I'm going to entangle this newly introduced physical degrees of freedom with the virtual degree or auxiliary degrees of freedom that I add on these legs to begin with, the ones that are used for the contraction of the PEPS. And this I do with these gauging transformations, with this unitary, actually controlled operations, which pretty much, if I want to make a hand-waving argument out of it, take what used to be the virtual field on these legs and make it physical. By this, I guarantee that if I add this virtual Gauss law, I will get the physical one. Okay, this is an example for U1, but what I'm getting here is something like this. If I started with a globally invariant PEPS, which fulfilled this symmetry property, acting on the physical equals acting on the 4 legs in some special way, after performing this gauging procedure, I'm going to get these 3 symmetry properties. Now I'm acting on, I have more physical degrees of freedom, and if I act on them in some particular ways, I will get that it's equivalent to acting on the virtual legs in this way that I have here on the right. If I use this procedure that I showed you, I will get these relations. And while this may show a bit out of the blue, let me show you why it's good. So now I have a state that I create like this. So it's not only the original PEPS ingredient, I also have the the initial states of the gauge field and the gauging transformations everywhere. And I have some new physical degrees of freedom for the gauge fields. And I want the state to be invariant under a local transformation. So I have some generator which is defined only on a single site. That means that I act on this degree of freedom, which is the matter, and the 4 gauge fields on the links around it. Now, since I gauged in the way that I showed you, I am going to use the symmetry properties that we have. So first, I can convert these 3 physical transformations to these 2 auxiliary ones, and then I can convert these 2 remaining physical transformations to these 2 auxiliary ones. The projectors are invariant. I never did anything to them. And then we get back the original state. So by doing this gauging in this particular way, we are getting out of a state with a global symmetry. We're getting a state with a local symmetry, which is a state that lives in the right Hilbert space of a lattice gauge theory. So this is the kind of a state that we would like to use for studying lattice gauge theories with tensor networks. So what we've worked with is a particular kind of states, which we call a locally gauge invariant fermionic PEPS or gauged Gaussian PEPS. What do I mean by that? Basically, I want to study theories where the matter is fermionic and it's coupled to some dynamical gauge fields. So my starting point has to be, if I want to use this gauging procedure, a state which describes only fermionic matter. I'm going to take some fermionic PEPS with a global symmetry for that, but I'm not just taking some arbitrary fermionic PEPS, I'm taking a Gaussian fermionic PEPS, which is the ground state of some quadratic Hamiltonian, of some free theory. Why am I choosing that? 2 reasons. First, it's really easy to parameterize these states and do everything analytically with them. But second, it's very similar to what you do in normal minimal coupling procedures. Normally, you take a Hamiltonian or a Lagrangian that describes a free theory, something which is quadratic, make the global symmetry local, and then the gauge field is introduced. So here we do the same. We start with a state which is globally invariant and describes free matter theory, and we perform this gauging procedure and get a non-trivial interacting state with local symmetry, which is something that lives in the right Hilbert space. So this is the starting point and the physical motivation for why we want to do that. So to begin with, long ago, we constructed some toy models for a U1 model and for an SU2 model. We constructed some minimal examples, and it's really easy to construct Gaussian states just by using some exponentials of creation of operators which are bilinear in the creation operators of all the fermionic modes that we have in our system, physical and virtual. I will not bore you with the details of how many fermions we need where, but eventually we can easily construct fermionic Gaussian PEPS that will satisfy the right global symmetries. We did it for U1, we did it for SU2, and we got some minimal cases which depend on a very, very small number of parameters. Then we applied the gauging procedure. We introduced the Hilbert spaces of the gauge fields and performed this gauging, and the parameterization of the original Gaussian fermionic PEPS survives. So what used to be translational invariance after this gauging, since we work in with so-called staggered fermions, this becomes charge conjugation symmetry, rotation invariance remains. And as I explained, what used to be the global invariance or the virtual Gauss law now becomes physical Gauss laws that are the cornerstones of the state of the lattice gauge theory. Then, of course, looking at it chronologically, and just to mention some important feature of such states, when we wanted to study these toy states that we constructed in the beginning and discuss some phase diagram, we used the cylindrical geometry. We put everything on the cylinder, and then we could effectively define a one-dimensional system. and define some transfer operator between the layers of the cylinder and study using the gap of this transfer operator. We looked at the gap of the, we deduced what happens to the gap of the parent Hamiltonian. However, what one has to be careful with when you deal with gauge theories is that if I consider this two-point function, two-point correlation of two operators on two different rows, it will be non-zero if and only if each of these operators is gauge invariant on its own. Otherwise, we would have to put what we call a string operator in between, something which carries some electric flux between what I have in the beginning and what I have at the end to ensure gauge invariance. And this means that we need to study a new kind of a transfer operator which carries electric flux. And this is quite an important ingredient in the study of transfer operators of gauge invariant PEPS. So yeah, with the toy models in this old works, we drew the phase diagrams from the transfer operators and found some, studied the decay of the Wilson loops, which are some non-local pure gauge order parameters, which tell us whether static charges in our theory are confined or deconfined. And in a later work, now getting back to the present, we actually went back to these special transfer operators which carry fluxes and could point out some connection between the spectrum of this special kind of transfer operators which carry fluxes to the decay properties of the Wilson loop, whether it decays with an area law implying confinement or with a perimeter law implying deconfinement. And back in the days with the toy models, we were actually able to see both kind of behaviors and draw some phase diagram. But it's much more interesting to see how we can actually use such states to study physics of a given Hamiltonian. Not only it's nice that we could construct states with the right symmetry and that we could study these toy states and see that they exhibit the physics that we expect. But the question is, how can we use them to study actual physical models? So for that, let's take a few steps back and discuss the physical Hilbert space of such a lattice gauge theory. So naively speaking, we would say that the Hilbert space is a product of two spaces, one of the gauge fields on the links, the other one of the matter fields on the sides. However, these two spaces are not independent of one another. They are constrained with the gauge invariance, with the Gauss laws that we have on each side. This means that the actual Hilbert space is some subspace of this product space, and one can actually use it in order to simplify what we're doing. So I'm going to define what I call gauge field configuration states like this. The Hilbert space on a link can be spanned by a basis whose elements are labeled by elements of the gauge field. So I can define these curly G states, which are just products of different group elements on different links of the lattice. So X is the starting point and K will be the direction of the link. And then I can write down this general integration over the group, something which resembles a path integral. What we have in a path integral, it's just the product of all the integration measures all around the lattice. So a general state of a gauge theory will take this form. As my state psi, I integrate over all the possible configurations of the gauge fields. I have some state of the gauge field and some state of the matter, which somehow knows or sees this gauge field in the background. The G here is some parameter. So if you want, this psi G, which is accompanied by this G, is the state of the matter when coupled to an external or a classical gauge field G. And since we have some gauge invariance here, of course, this psi of G will have some special structure. And if this psi is a fermionic, is a gauge Gaussian Fermionic PEPS, this states psi of G will just be fermionic Gaussian states, very, very simple states to handle. And this allows us to perform to do some numerical computations very, very easily. Why? Take, for example, the Wilson loop operator. The Wilson loop operator, if I'm going to choose the U1 case, I really don't want to get into these details, but in U1, I have this, on each link, I have this e to the I phi operator, something which behaves like an element of the U1 group. And the Wilson loop is just a product of these operators along some closed path. If I want to compute the expectation value of this operator for such a state, I can simply see that these configuration states are going to be eigenstates of this operator. And then I can just convert it to some integration over this e to the I phi. Now, these are not operators. These are numbers which I get by this eigenvalue relation. And I just need to integrate over the group elements. And I'm getting here something that I can compute using some Monte-Carlo. I have some P of phi here, which is a probability density. It is simply something that I get out of integrating computing the norm of my Gaussian state. This I can compute pretty easily and efficiently, divided by this so-called partition function, which is the integral over all these things. So I can generalize it to any group that I want. And if I want to compute the expectation value of a Wilson loop, I can simply write it as group integration over some function of the group elements per configuration multiplied by this probability density that I can compute easily using the norms of this psi of G, these Gaussian states. So then I can actually use Monte-Carlo to compute the integral. And with this Monte-Carlo, I will have no sign problem because the probability density, unlike in the Monte-Carlo used in conventional lattice gauge theories, which is the result of exponentials of the action, here it's something that I get from the norm of a state. And the norm of a state will always be real and positive. So the sign problem can't happen here. And I can do Monte-Carlo in order to solve it. And this can be generalized to all the physically relevant operators that one is interested in when studying a lattice gauge theory. This can be some things that we call electric field operators, which also depend only on the gauge fields, and also some operators which depend on gauge fields and the matter, the fermions, which we call mesons. And this will also depend on the covariance matrix of each Gaussian state in the expansion, but the covariance matrix elements are also very easily computable. So we can really use Monte-Carlo to efficiently compute, contract the PEPS and compute these correlation functions and expectation values. Then the only question that one has to ask, and it's a huge question, is are these states actually physically relevant for anything? So we started with a simple check in which we had another look at the toy models from the beginning and computed some expectation values of some gauge invariant operators using this method, and saw that we could reproduce the same phase diagram. That's not a big deal. But here comes the interesting thing. The first benchmark that we did, the paper that was out 2 years ago, in which we took the Hamiltonian of an actual lattice gauge theory, of a pure gauge Z3 lattice gauge theory, and studied it using this method. And we got the following results. So here I'm looking at the expectation value of the Hamiltonian for a small system of 2 by 2. And here in blue, what we have is an exact diagonality, the ground state energy when you perform an exact diagonalization. It's a small problem, so it's not a big deal. Then we start using these PEPS as an ansatz, using this variational Monte-Carlo that I introduced, with several layers. And by layers, I simply mean adding more virtual parameters to the PEPS, or if you want, increasing the bond dimension. And we can see that the more layers, the more parameters, the larger the bond dimension is, we can really approximate very well the ground state using these states. So this is a really nice benchmark that shows the power of these states. And of course, from this exact construction, we could go to larger systems of 2 by 2, 4 by 4, 6 by 6, 8 by 8, and actually use this Monte-Carlo computation instead of the exact contraction up here. And as you can see, we got really nice results. So the states actually approximate very nicely the ground states of this very real theory and can be used as an ansatz. And I was hoping to be able to talk about it today, but we're still dealing with a few numerical obstacles. But very soon I'm happy to announce that we will have some nice new results of another gauge theory, and with an improved algorithm that runs faster. I didn't get into some problems in running the algorithm, but something which runs faster. Basically, I will tell you that it means calculating less Pfaffians. And we are getting some really nice fits of the Monte-Carlo computations with what we could compute for small systems, and we can extend it very nicely to larger systems. So I really hope that very, very soon I will be able to show you some more about it. And to me, it's really exciting because, as you saw, this has been a very long going effort, and we are starting to see some fruit out of it. So to conclude, what I hope that I managed to show you today is that PEPS can be generalized to describe lattice states with a local gauge symmetry, which live in the right Hilbert spaces of lattice gauge theories. Using the construction of the PEPS in a way that comes quite naturally in the PEPS construction, it's possible to gauge or to minimally couple matter states with a global symmetry and make them locally gauge invariant, and properties of these states survive or get modified of the original states into the local gauge invariant state. We could see it very nicely in examples that we constructed, but this is also the gate of a lot of interesting analytical and mathematical work that still has to be done, and we're still going to do, which studies all these things more rigorously. But in parallel, what we could see is that one can combine it with some really nice and efficient numerical method, which actually includes variational Monte-Carlo. The observables and the correlation functions can be computed quite efficiently. And we've been able to see so far quite a few nice benchmarks of how these states are actually physically relevant and work for physically interesting gauge theories. And yeah, with this I conclude, and I really hope that you heard everything I said so far. So thank you very much. Thank you. So the real numerical bottlenecks for this method, I would say the things that we were sort of stuck with in this DET3 work that I showed you is that sometimes we needed, in order to compute some observables, we needed to compute Pfaffians of matrices with size scale like the size of the system. And this is a serious bottleneck because it's Pfaffians are not really something that you can compute efficiently. And in this new work, we were able to sort of get rid of that and convert these global Pfaffians to Pfaffians of small matrices, or let's say matrices which change very locally, so we can do things with some local updates. So these are the things that I hope to be able to report about soon. Now, about 3 space dimensions. So yeah, I would say that it's not a big deal to generalize it, because the scaling of this method with the dimension is very indirect. It's just a consequence of it depends on the dimension through the size of the system. Basically, the question is how many links we have, and it doesn't matter if they extend on a line or on a plane or in a 3-dimensional setting. So there is nothing serious which prevents us from going to higher dimension, and this is one of the things that we are going to do next. About non-abelian, I saw the question now. So yeah, the theory exists. You can compute everything and parameterize state for non-abelian theories in exactly the same way. And the only thing that has to be done is that we need to play with the Monte-Carlo sampling and make sure that this is done efficiently. But here, of course, we can use sampling techniques and tricks that are used in the, from the other side of using Monte-Carlo in lattice gauge theories. So basically, there is nothing, let's say, essential which prevents us from looking at non-abelian theory. So yeah, if everything works well, this is what we're going to do. And these questions are pretty much our plans for the future. Okay, so thank you very much for listening to me. And once again, I'm truly sorry, and I hope to see you all real soon, for real and in person. And yeah, thanks a lot, and have fun the rest of the workshop. Thanks.